Alright, just a few more seconds. I'll stop at 50. That's everybody. Alright, good. C is the right answer. You just have to have a continuous path, right, for the electricity to flow, where it plays through the battery, through the light bulb, through the little filament, and then to the negative side of the battery. You have to have a continuous path.
So, I don't know, talking on the light bulb, I didn't know this from guessing the little metal part where it screws in. That's like one of it, but that's...
Right, there are two parts to it. It's what I'm drawing here, where light bulbs is a resistor. They're not directional. That means it doesn't matter which way you put them in. You know what I mean?
Yeah.
Like some things like capacitors, LEDs. Well, no, not capacitors, but LEDs. Some capacitors do, I guess. But LEDs and diodes and stuff are directional, so it depends what direction you put them in. Anyway, yeah, so the electricity would flow in the little part on the bottom of the bulb, and then it goes through the filament, and then it comes out the metal casing where the thread goes. Are you double? Oh shoot, we haven't got. This is good. You double the voltage across a certain conductor, and you observe the current increases 3 times. Which of these can you conclude? Is Ohm's law obeyed? Ohm's law is not obeyed, or it's not relevant? More seconds. Stop at 110. 110. We're missing one person up there. Okay, very good. Here, Ohm's law is not obeyed because since V is equal to IR, if I double the voltage, then I should double the current. It's a direct relation. This type of device would be called non-ohmic. We're going to get into that today a little bit. Non-ohmic just means it's a device that doesn't follow Ohm's law. So we'll talk about this in just a bit. 2 wires. Let's see, have we gotten into this? No, we've just done Ohm's law. All right, we'll come back to this in just a bit. By the way, we won first place this weekend. If y'all care? You don't care, Hunter? You don't care?
Oh, I think you said if you here.
Oh, I said if you care.
Oh, I didn't hear that.
Oh, okay. It's okay. You don't have to care. It's fine. All right. Let's see. We did Ohm's law. I want you to know what ohmic versus non-ohmic means. You sort of need to know this, that if something doesn't follow Ohm's law, then that's considered non-ohmic. Most devices are ohmic, except for things like diodes and what have you, and those are non-ohmic. So materials that do follow Ohm's law are called ohmic. For non-ohmic materials, the resistance of the material will change as V and I change. So if I plot I versus V for an ohmic device, it looks like this, where the slope is equal to the inverse of the resistance. Y'all did this in lab. Where the slope is equal to 1 over R. A non-ohmic device might look something like this, where the slope can change, and that means that the resistance of this device will change, depending upon what is the current or the voltage in it. So, for example, diodes are a type of a non-ohmic device, and the resistance in a diode will change. If the current is flowing in one direction, then the resistance is just whatever it is. But then if it tries to flow in the opposite direction, so if it has a negative current, then the resistance will go way up. So for example, let's say for a diode we were to plot, let's make this current, this would be plus I, this would be minus I, and on this axis we have the resistance. If for a normal current it would have a resistance that would look like that, and then for a negative resistance a negative current, resistance would go very, very high. So what this does is it acts as a gate for electricity. It allows electricity to flow one direction but not flow in the opposite direction. All right, so a diode is just one type of non-ohmic device. Let's try this little quick test. So you just need to know if it doesn't follow Ohm's law, that's called non-ohmic. And then also diodes are this gate for electricity, where in one direction the resistance is some normal amount, in the opposite direction it basically goes to infinity. All right, about 10 more seconds. I'll stop at 45. 45. He is right. That's good. We had this question just now, right? So if I have 3 volts and I apply it to the device and I get 2 amps, and then if I double the voltage, if it's an ohmic device, I should get what current? I should get 4 amps. So if I double the voltage, I should get double the current, but here I don't. I get 1.5 times the current. So that's a non-ohmic device. B is the right answer. Okay, we watched the magazine video about resistors. Is that right? Yeah, okay, that's this one right here. Let's look at resistivity. Now, when we think about electricity, we can sort of think of it as in terms of a water analogy, where I have water flowing in pipes, and that holds actually in a lot of the circuits that we'll look at, that water flows through pipes with a source that's pumping it, and it goes through the pipes with different radii. It'll act a lot like electricity. So when we think about water flowing in pipes, we can think about the resistance that those pipes will give to the water flowing through them. And as far as the geometry of the pipe, and electricity acts in much the same way. So let's think about how electricity, or water, if you want to think about it in those terms, how it depends upon the length of your pipe, or your resistor, and also the cross-sectional area of your pipe. So let's imagine that if I let the area of my device go up, whether I'm thinking about water flowing through a pipe or electricity flowing through some electrical device, wire, piece of material, whatever. If I let that get bigger, does the resistance go up? Does the resistance go down? Or does the resistance remain the same? So if the area increases, what happens to the resistance? Remember, the resistance is that resisting the flow of electricity. So if the area of my device gets bigger, whether I'm thinking about a pipe with water flowing through it or a piece of metal with electricity flowing through it, it's going to be the same. If my area increases, will it be more resistant to the flow of water or electricity? Will it be less resistant, easier to push it through, or will it be the same? What happens to my resistance? All right, very good. Everybody has the right answer. I think we're missing one person out there. I'm going to stop at 40. Let's see here. Somebody stuck it in there, huh? All right, B is the right answer. All right, if I increase the area, it's easier to push electricity or water, if we want to think about it that way. Now let's imagine now, what if my length goes up? What happens to the resistance? Does it go up, down, or does it stay the same? So I make this pipe longer. What happens to the resistance of that pipe? Is it harder to push water through it, easier, or does it remain the same? And then the same will also be true for electricity. Have a short piece of pipe or a really long piece of pipe? All right, I'm going to stop at 40 seconds. 40. All right, we're sort of split here. Let's see, some of you said it remains the same and others said it goes up. Imagine that I have a hose, right, like a water hose, and I have a hose that's just this long. I want to put water through it. I don't need a whole lot of pressure to put water through it, right? Because it's just a little bitty hose. But then if I have a 100-foot hose, is it going to require more or less pressure in order to force water through that 100-foot hose? It's going to require more pressure. So when you increase the length of a device, then that increases its resistance. That's true for like water flowing through a pipe. It's also true for electricity flowing through a piece of metal or a piece of wood or whatever it is you're trying to put it through. So whenever you increase the length, then that increases the resistance. All right, so we have these two relationships. The resistance is proportional to the length, and the resistance is proportional to 1 over the area. There's also another relationship between that's dependent upon the material, and that's called the resistivity. And the resistivity is directly proportional to the resistance. So some materials will have a high resistivity, and some materials will have a low resistivity. So among these two, which of these, A or B, would have the highest resistivity? That is, a piece of copper or a piece of wood. Which of these has the highest resistivity? A copper or wood? Now remember, the resistance is proportional to resistivity, directly proportional. Resistivity, by the way, is measured experimentally. I think y'all done that in lab, where you measure the resistivity for certain devices. A piece of copper, I think you did that. All right. So, is the resistivity for copper high or for wood? Which of these has the higher resistivity? All right, very good. Just about 5 more seconds. I think that's everybody. I'm going to stop at 34. Okay, which of these has the higher resistance, copper or wood? Wood has the higher resistance, so it also has the higher resistivity. Copper, it's a metal, it's a conductor, has a very, very low resistivity. That's why it's a big conductor, because it has a low resistivity. Good way to determine unknown metals. If you have a metal and you don't know what it is and you can't figure it out, you can measure its resistance and then measure its dimensions and determine what is its resistivity. And those are well known, they're tabulated. So if you have an unknown metal, you just want to know what it is, and you can't tell from its color or its malleability or whatever, then you can measure its resistance, and that's a nice way to find unknown metals. We'll work some problems like that a bit. So we can combine these. We get the resistance is equal to the resistivity times the length over the area. So now we have two different ways to find the resistance. We have Ohm's law, V equals IR, and that's how we define the resistance. But then we can also find the resistance based on its dimensions. We had this for capacitors, remember? We had the Q equals CV, and that's how we define the capacitance. But then in addition to that, the capacitance dependent upon the geometry of the device. So here, our resistance will also depend upon the geometry of the device. Let's work a couple problems. We'll see some more of these in just a bit. Well, let's say that two wires, A and B, they're made of the same metal and they have equal length. but the resistance of wire A is 4 times the resistance of wire B. How do their diameters compare? Let me remind you, resistance is rho L over A. And so resistance is rho L over pi d squared. It's actually pi r squared. I'm just going to call it pi d squared to make it more simple. Right, so how do these diameters compare? Whenever I encounter these, I always think about which wire is smaller. I know that resistor A has the bigger resistance. So then how do their diameters compare? Or resistor A be bigger or smaller than resistor B? So I know that resistor A has 4 times the resistance of B. So is it a bigger or smaller wire? And then if it's bigger or smaller, by what amount? Okay, y'all are doing pretty well. A lot of you have eliminated some of the wrong answers, right? Because if I know that the resistance of wire A is 4 times the resistance of wire B, that means that it's a bigger or smaller wire. If it has a bigger resistance, that means it's smaller. So it's harder to push electricity through that wire. So that just limits it to 2 answers. Which ones are they? Right, either D or E. So that gets rid of A, B, and C. Because I know that resistor A, this will be A, it has a bigger resistance. That means that it's going to be smaller. So now I want to know, how do their diameters compare? I know that in this term, I need to get a factor of 4 over here. How am I going to get a factor of 4 if their diameters are different? Will I have a factor of a half or a factor of a quarter? I think about that and put in the final answer. Y'all are sort of split. We know that it's either D or E, and right now about half of you are putting D and half of you are putting E. I need to put a number here that'll give me a factor of 4 over here. Remembering that this is squared. Alright, that's a lot better. Just a few more seconds. I'm going to stop at 3:05. It's like everybody's got the right answer now. Right, B is the right answer. So y'all had a lot of help, but you've done it really well. So, sort of run out of good jokes. Let's see. What did the hammer say to the drill? Say, I don't know what. You're really boring. Like at Boar's house. Okay, alright. A little girl told me that one. Alright, the current of 20 amps flows through a wire of length 1 meter and cross-sectional area. Potential is that. What is the material of this wire? So again, if you have an unknown material, if you know its dimensions, it's pretty easy using a micrometer to measure the dimensions. You can find out what is that by calculating the resistivity. So try this out, find the resistivity, and then you can just select it from this table. What is that unknown material? Really nice way to find unknown metals, identify unknown metals. right, about 10 or 15 more seconds. Ask your neighbor if you're not sure. I'm going to do 5 more seconds. 3:35. All right, D is right. These are pretty straightforward. You just need to put in the right numbers and calculate what is rho. So here I know that R is rho L over A. So I calculate rho, which is R times the area over the length. The resistance I find from Ohm's law, that's V over I, which is 1.4 over 20, which is what, 0.07, is that right? So 0.07 ohms times the area, which is 7.85 times 10 to the minus 7, divided by the length, which is 1, and then you find the resistivity, and you find it's 5.5. What's that? Okay, yeah, 5.5 or 5.495 times 10 to the minus 8, which you find is tungsten here. Right, so D is the right answer. You can see something like that as a free response on your test, which is in 1 week. I realize that, right? 1 week from today. All right. Yeah, not only did we come in first place like our team, but one of our 7th graders came in 2nd place overall. And usually, like, it's the 8th graders, but we don't have any 8th graders on our team yet because we don't have 8th grade yet. And one of our 6th graders came in 6th place overall. Yeah, that's pretty good. Josie Fungi was our 7th grader. And Jackson Landry, yeah. No, I gave the area here. So, yeah, if I gave you the radius, you'd have to do pi r squared, or 1/2 tau r squared. Right. Yeah. Is that clear, Daniel? Yeah. All right. Let's see. We talked about this a little bit. It'll come up a bit more in the next chapter, but we can think about an electrical circuit as being a water system. Or if you want to think about it too, as like your as like a circulatory system in your body, where you have a pump right here, and that's going to be analogous to our energy supply. Remember, potential is just energy per charge. So we think about our charges coming here and then gain energy because it's a source of potential, which is energy per charge. And so that power supply or that battery or whatever it is, it increases the potential energy of the electrons as they go through the circuit. We can think about this too, like I said, like the circulatory system in the body. You have to take an anatomy yet? Or y'all don't take anatomy, do you? Nobody? Okay, yeah. Well, in the body you have the heart pump, right? And it sends blood out into the body through the aorta, and then that blood goes out into the body, and then it comes back through the vena cava, which is the vein coming back into the heart. Where do you think, which of those, the aorta or the vena cava, have the highest pressure, or the highest amount of energy in the blood? The first one, the aorta. That's analogous to this part, where the electrons have the most energy, or to this part, right after it leaves that pump, after all that fluid has gained all the energy that it needs, or all of its pressure, and then it goes out into the circuit, or the body, or whatever, however you're thinking about this, and uses that energy to do whatever it is that you want it to do. And then it comes back, and here it has very little energy until those electrons are pumped back up by the power supply. Now, if you have resistors in parallel, they'll look like this. We can think about this in a couple of different ways. First of all, they're all going to see the same amount of energy coming from this pump. That might not seem obvious to you right now. We'll talk about it in terms of resistors in just a bit. But more importantly, if I had the same amount of energy, which of these is going to see more water flow? The bigger one. The bigger one will see more water flow. So this is like the one with the lower resistance, and so it's going to get more water flow. Similarly here, this resistor will still see the same amount of energy from this battery, but it's going to get a larger amount of current if it has a bigger, or excuse me, a smaller resistance, like this part of the pipe. We'll get into this with circuits in the next chapter. So here, the one that gets the most water flow is the bigger pipe. With the smaller resistance. Alright, it resists the flow of electricity less, so it gets more current flowing through it. Alright, let's talk a little bit about power. This is going to come up again in the next chapter when we do household circuits. But batteries convert chemical energy to electrical energy. And then that electrical energy is then converted to whatever it is that you want to do. It can be converted to mechanical, which is common. Say you have an electric motor where you have an electric current that will cause something to turn. Or it can convert it to thermal energy, like your hair dryer or your bathroom heater. Alright, so since we're really just talking about energy, we want to talk about also the power of devices. All of your devices in your house, for example, that you use, they all have a power rating. So for example, your hair dryer or your bathroom heater, that's a pretty high power device, about 1,000 watts. Your refrigerator is maybe about 300 watts. And then something like, your radio or whatever, that's a very low power rating, maybe 8 or 10 watts. So we can get an expression for energy pretty simply. Our change in potential energy we've already defined as being Q times delta V. Remember this delta V, this voltage potential difference, this is energy per charge. So if I multiply by a charge, then I get energy. And since power is just energy over time, and that's going to be Q times delta V over delta T. But since we know that current is Q over T, then I get our expression for power, which is just V times I. So our power, uppercase P, is equal to V times I. And this is sort of one of those basic equations that electrical engineers and electricians use to determine the current flowing through a device or define the power of a certain device. The unit of power is the watt. We used this last semester when we did work and energy. Remember, power is work over time. 1 watt is equal to 1 joule per second. And then we can have this expression written in a couple different ways. I know that P is equal to VI, but I can do substitutions from Ohm's law, and I get P is equal to I squared R. Or also P is equal to V squared over R. These are both on your equation sheet, and they come up in various times. So I'll show you some questions next where you might want to use one or the other of these depending upon what is being held constant. Let me just show you some questions. I think it'll be more obvious, but this just comes about from substituting this. So if I say V is equal to IR, plug in IR for V, then I get I squared times R. Or if I say I is equal to V over R, I plug that in here, then I get V squared over R. So these are just substitutions into that P equal to VI. They're the same equation. They're both on your equation sheet, so if you forget them, you'll have them. But like I said, they just come about from substituting. Let's do a few questions. Alright, two wires A and B are made of the same metal and have equal length. The resistance of wire A is 4 times the resistance of wire B. How do their diameters compare? I'm going to stop at 35. 35. Okay, this is identical actually to the other question that we had. So if it's 4 times, that means that it has to be half the diameter. So that's 4 times the resistance, that means it's smaller, so that gets rid of A, B, and C. And in order to get that factor of 4, because it's the diameter squared, you have to have a factor of a half. A half squared is, or 1 over a half squared is equal to 4. Right, a wire of resistance R is stretched uniformly. That means that it keeps its volume constant until it's twice its original length. What happened to the resistance? Let me draw a picture to explain to you what happened here. I have a wire, and it's stretched out. That's the way they make wires, right? They take a big piece of metal and then they stretch it out. So it gets skinnier, but it gets longer, so that the total volume is constant. And I want to know what happened then to the resistance of this wire. If the total volume remains constant, the total amount of material in this metal remains constant, then what happens to the resistance? I'm increasing its length by a factor of 2. All right, folks, everybody has it wrong. So let's think about what happens here. I'm increasing the length by a factor of 2, right? And so that would increase the resistance by a factor of 2. But I'm also doing something else, right? When I stretch out this wire, it gets longer, but it also gets what? Smaller, right? It gets smaller in diameter. And so what I want to know is what happens to the area of this, and how is that going to affect the resistance? Right? How much is the area going to decrease when I stretch out this wire? Alright, so D isn't the right answer. It's not just a factor of 2. If you were just increasing the length by a factor of 2, that would increase the resistance by a factor of 2. But because the area is also changing, D is not the right answer. All right, I'm going to stop at 225. 225. Still sort of around all over the board here a little bit, but. All right, but E is the right answer. It could have been keyed off because I know that if I decrease my area, that also causes the resistance to go up, right? If A goes down, that means that the resistance goes up. And so, since we've already eliminated this answer, it has to be this one, right? It has to be 4. But if you're not certain, you could also think about the volume remaining constant. So, keeping its volume constant. That's just a fancy way of saying that the amount of metal that you have in this material is not changing. So the total volume is the same. And remember, volume is equal to area times length. So if I increase my area, or excuse me, if I increase my length by a factor of 2, if this volume remains constant, that means my area has to go down by a factor of a half. So as you're stretching out this metal, making it into a wire, you make it longer by a certain amount, and then you decrease its area by the same amount. So I get a factor of 2 in the length, and I get a factor of a half in the area, and so that gives me 4 times the resistance. Can you follow that? Yeah? When you rotate the knob of a light dimmer, what's being changed in the electric circuit? You know, a light dimmer, the little thing that you change the light to go bright or dim. When I was a kid, my mom cleaned houses, and so during the summer I'd go with her to all these houses that she cleaned in the summertime when I was out of school. And some of them would have these light dimmers, and I used to like to go and just dim them, because I thought it was really novel. I thought they were all like rich people and they had light dimmers in their houses, and cable TV. But it's okay to have light dimmers. I mean, I don't have one in our house, but it's not like you're a bourgeois if you have a light dimmer. what's being changed in the light in the circuit when you rotate the knob. The power, the current, the voltage, A and B, or B and C. I've mentioned this, but in a house, in a household circuit, all the devices operate at 120 volts. We'll see that a little bit later. But in a house, all the devices operate at 120 volts, the way that it's laid out. All right, just a few more seconds. Stop at 135. Okay, let's see. A and B, both the power and the current are changing. I know that power is equal to V times I. And the power, that describes how bright it is, right? A 40-watt bulb is not nearly as bright as a 100-watt bulb. So when I'm changing the dimmer on the switch, I'm changing the amount of power that I'm getting out. But if the voltage is constant, that means that the current has to be changing. So both the current and the power are changing. There's actually another thing that you're changing. What is that? This is actually what you're physically changing, which results in the resistance, right? So you're actually changing the resistance. You have a variable resistor inside of that switch, and when you change the resistance, then that changes the current, which then changes the power, which affects what you see. The power changes, which affects the brightness of the bulb. Two bulbs operate at 120 volts, but one has a power rating of 25 watts, while the other has a power rating of 100 watts. Which one has the greater resistance? Is it the low power rating or the high power rating? 25 or the 100? Or do they both have the same? Or is that not relevant at all? Okay, doing really well. Just a few more seconds. I'll stop at 110. 110. A is the right answer. The one with the lower power rating has the greater resistance. You can think about this in a couple ways. The one with the lower power rating, because P is equal to VI. If you have a low power rating, that means you have a low current, because V is always the same, right? And the one with the lower current must be the one that resists the flow of electricity more. That's going to be the 25 watt, or the 25 watt and will resist the flow of electricity more. That means it has a bigger resistance. You can also think about this in a similar way, but if I have this device that's not very bright, or not as bright as another, that means I don't have as many electrons carrying their energy through that wire, and if I don't have as many electrons, that means that has a greater resistance. Next one. Two space heaters. One has twice the resistance. Which one gives off more? Heater 1, which has the bigger resistance, Heater 2, which has the smaller resistance, or are they both the same? They're both operated at 120. All right, the one that will give off more heat is the one that allows more electrons to flow through its element, its heating element, which is basically just a wire. Which one then will allow more electrons to flow through its element? There's a few more seconds. Stop at 102. Okay, B is the right answer. The one with the lowest resistance allows the greater amount of current, and when there's more electrons, I get more energy. Have you ever looked inside of your heater at home, or like a hair dryer? What do you see inside of it usually? Right. Right. When it's running, it's red, but it's just a coil of wire. The same in a hair dryer. What's that, Doug?
I was just gonna say the coil of wire.
It's just a coil of wire. So the same, like when I get up in the morning, I'm blow drying my hair. It takes forever. I don't blow dry my hair. I have to make, but it does. But a hair dryer, if you look inside of it, it just has a coil of wire. It's a lot like that. It is that. Right? So very high currents. That's why they can be dangerous in wet bathrooms, for example. All right. One more thing, or a couple more things. Probably go and wrap this up now. These are some sample MCAT questions. None of y'all are pretty mad, but these are pretty simple. If a current of 1 amp flows through a circuit of 5 seconds, how much charge is flowed? Just remember our definition for current, I is equal to Q divided by T. And then if I want to find the charge, that's I times T. If I have a current of 1 amp for 5 seconds, that means that I'm getting 5 coulombs of charge passing a point in a given amount in that 5 seconds. So that's based on our definition of what is current. If I have R, the resistance, for 2 identically shaped conductors, so say a piece of copper and a piece of steel or whatever, but they're the same shape, they have the same length and area, and their resistances are in a ratio of 1 to 2. What ratio are the resistivities? How do they compare? Everything else the same, how do the resistivities compare? All right, it is, yeah. So R is directly proportional to the resistivity. So what did you say? It's also going to be 1 to 2, right? So another way of writing this would be to say R1 is equal to twice R2, or vice versa. And so similarly, rho 1 will equal to twice rho 2. Right. It's a linear relationship. It's a linear direct relationship. Whereas with the area, it's an inverse relationship. Right? Resistance is proportional to 1 over the area. All right, let's talk about this. We're going to come back to power, and we'll talk about household circuits and sort of how electricity gets into our homes in the next chapter. But let's think about this because it's related to power. Y'all know what a transformer is? You've seen transformers, right? Transformers in a lot of places. You probably think of the one outside of your home, right? It's like a big metal can. It's actually filled with oil, and then a lot of metal plates inside of it. We'll talk about how those work next chapter. But what a transformer does is it takes an input voltage and it makes it into a different voltage. It transforms it into a different voltage. So for example, the transformer cans outside your house, they take a very high voltage, which is about 3,000 or 4,000 volts outside of your home, that comes in those lines coming next to your house, and then it transforms it into a lower voltage of what to come into your home? 120 volts, right. So it transforms that 3,000 volts into 120 volts. And then if you look at your house, the wire that comes into your house connects up to that transformer. And so it takes that 3,000 volts, connects it to, or transforms it to 120, and then brings it into your home. But that can doesn't really do anything, right? There's no power source inside of the can, or nothing there that actually takes energy away from the electricity. So then what happens, how can you explain that in terms of energy? If I'm taking something 3,000 volts and converting it down to 120 volts, what happens to that energy? No, it's not like a capacitor. It doesn't store energy in any
It's
way.
a resistor.
Something on the doesn't get bigger.
The power something else has to get bigger, right?
Power
And
doesn't.
the power doesn't change. So what else is getting bigger? The voltage is changing, but the power is not. So the current is different. Right, so V equals VI. So in your power line goes a very low current, but into the electricity that you get in your house, what happens to that current? It goes up. So we can think about it in this way. Our power is equal to VI. This power has to remain constant because you're not adding energy or taking energy away in any way through the transformer. It's entirely how is it right to say it's passive? Like it doesn't do anything to the charges. Right? It just changes their voltage, but it also changes their current. So the total amount of energy remains constant. The voltage for your transformer in this case will go down, and so the current has to go up. This is for your household transformer. Now in this problem, V out is actually 300% larger than V in. So this would be a step up transformer. It's stepping low voltage up to high voltage. There are other places where you have transformers in your house. Where are they? Seen transformers in your house? No, circuit breakers are different. Those little black plugs with a big square on the outside of the plugs, that's a transformer. It takes your high voltage electricity and converts it into low voltage electricity. They also generate DC current, which is a little bit different, but it's like a transformer as well. So let's see, here I have my voltage is going up because my V out is equal to 3 times V in. That means that my current is going down. So what is the ratio of I out to I in? So if V out over V in is equal to 3, what is the ratio of I out to I in? It's going to be 1 over 3. So if I get a factor of 3 here, then I have to get a factor of a third here. I get a higher voltage but a lower current. Well, let's try this quick test. I think we might have one more after this. Let's just do this one. Which light bulb in your house draws more current, a 40 watt or a 100 watt bulb? It's a very similar question to this before. So there's a few more seconds. Stop at 38. Very good. B is right. The more power means you have more current. So the 100 watt will draw more current. A 50 ohm resistor is hooked up to a power supply of 150 volts. What is the power dissipated? Remember, P is equal to VI. We had those alternate expressions as well. P squared over R and I squared R. We'll make this the last one. Guys, we're going to move on to the next chapter next time, and we'll talk more about this later. The test, I think this will include a small part of the next chapter, just the easy part, like some of the easy circuits at the beginning. Right? But more about that later. We'll have some time on Friday to review for the test as well. All right. Looks like most of you are almost there. So I'm going to give you 5 more seconds. Stop at 110. All right, A is right. Since we have V and R, we could just say V squared over R. That's 150 squared over 50, which is equal to 450 watts. You could also calculate the current. The current is 3 amps, and then say V times I. Have a good day, okay? We'll do that last question next time. But then we're going to move on into the next chapter. All right. Have a great day.